So what we have gone through in the previous class, so we solved two problems on potential energy method. After that we started with interpolation model. What are interpolation models? What are interpolation models or interpolation functions? These are nothing but displacement models or trial functions which are mainly used to determine displacement variation within the element. In general, I am speaking. Then in the previous class we even went through how to write the polynomial functions. You write interpolation models are of two types, right? Polynomial function and trigonometric. In the previous class we have gone through how to write a polynomial function for a given element type. Okay, if it is 1D, if it is 2D, if it is 3D, and if it is a linear model, what should be the polynomial equation? If it is a quadratic model, what should be the polynomial equation? Okay, then if it is cubic model, what is the equation? And we also went through what is simplex, complex and multiplex elements. Now today we'll move further. Okay, now in today's class what we'll do is, in the yesterday's class you have gone through simplex elements, right? What are simplex elements? Those contain only boundary nodes and have only constant and linear terms in the polynomial equations. So all those three equations are written to you on your screen for 1D case, 2D case and 3D case. So u of x equal to a0 plus a1x is your 1D simplex element, okay, linear equation, and that is your 1D element, okay, and this is your 2D element, and for that your polynomial equation, and similarly for 3D element, okay, a0 plus a1x plus a2y plus a3z. We will be using these three polynomial functions, okay, in order to derive what are the shape functions for the given element 1D, 2D and 3D case, okay. So before that we'll go through what are the selection points. Before you select any polynomial function, what are the points to be considered, okay, while choosing the order of polynomial type of interpolation function? Following considerations to be taken into account. What are the points? The interpolation model should satisfy the convergence requirements, okay. So what are these convergence requirements? We'll go through once we finish all the derivations. Before winding up the module 1, we'll go through what are convergence requirements. So whenever you choose any polynomial function, it should satisfy that convergence requirements, okay. And the pattern of variation of field variable resulting from the polynomial model should be independent of the local coordinate system, okay. So when whatever the pattern variation of the field variable, whether it is displacement, temperature, it should be independent of other coordinate system, okay, especially local coordinate system, okay. What is local coordinate system? We will see it in the next slide, okay. And the number of generalized coordinates should be equal to the number of degrees of freedom of the element. What are these generalized coordinates? You are writing these equations, right, for polynomial functions. a0, a1, a2, what are these? These are constants. So here these constants are called as generalized coordinates. So these generalized coordinate, number of generalized coordinates depend on number of degrees of freedom of the element, also on the number of nodes. Now how many nodes are there for this 1D case? 2 nodes are there. So how many generalized coordinates? 2 generalized coordinates. Also we are considering that there is 1 degree of freedom per node. So there are only 2 generalized coordinates in the equation 1D case. Similarly here in the 2D case, 3 nodes are there, and we are assuming that only 1 degree of freedom is there per node. So if it is 1 degree of freedom per node means a0 plus a1x plus a2y, only 3 terms, okay, 3 terms. So number of degrees of freedom are 3 per one each node, and this is the equation, okay. And for 3D case there are 4 nodes, so 4 generalized coordinates, okay. Number of degrees of freedom are equal to number of generalized coordinates, okay. You should know this. So these are the points to be considered while selecting any interpolation function, okay. It should satisfy the convergence requirement. Variation should be pattern of variation, okay, whether it is linear, quadratic, it should be independent of local coordinate system, okay. And number of generalized coordinates should be equal to number of degrees of freedom. You can take down this. Just wait for a few seconds, then we'll move on to the next slide. Shall I move to the next slide? Yes.
Yes, sir.
Should I move to the next slide?
Yes, sir.
Okay. So coordinate systems. So how many generally how many coordinate systems are there, generally speaking? Which are those? It's been written here in the first line itself. Generally, coordinate systems are of two types. Can you tell me which are those two types generally coordinate systems?
Cartesian coordinate and polar coordinate.
Cartesian coordinate and polar coordinate. Cartesian is also called as global coordinate system, right? Okay, Cartesian coordinate or polar coordinate system. But in FEM there are three. Which are those? Global coordinate system, local coordinate system, and a natural coordinate system. So what is global coordinate system? It is similar to your Cartesian coordinate. Okay, it corresponds to the entire body and used to define the points in the entire body. So whenever you define the nodes for the given element, okay, for example, it has been given here. So this is your coordinate, general coordinates, global coordinate, x and y, and this is the element, okay, which has been divided. This is your body, which is a plate, and which has been divided into number of elements. Okay, and this is numbered with respect to what? Your global coordinate x and y. Okay, global coordinate x and y. Got it? Global coordinate x and y. This is your normal Cartesian coordinate only. Now what is local coordinate? It corresponds to a particular element in a body. Now consider the same example here above. If I take this element, it is 1 and 2. Known numbers are 1 and 2 for this element 1. Okay. If I consider it with global coordinate system. Okay. So here, while denoting the global coordinates, so we denote it by x and y. While denoting the local coordinate, we denote it as x dash and y dash. Okay. Now if you see here, if I consider it here, it corresponds to the particular element in a body. Okay, it corresponds to the particular element in a body. Locally it has been considered. Okay, locally it has been considered. See here. So this element, especially this element 2, is being considered with respect to x and y here. But here, when you consider it with locally, it has not been considered with respect to x and y. Locally, okay, locally, say x dash and y dash. This about local coordinate system, clear concept you'll come to know once we start deriving the stiffness matrix for truss element. You'll come to know what is the difference between a global coordinate system and local coordinate system. Okay. And what is a natural coordinate system? It is also a local coordinate system in which a point within an element will be expressed by dimensionless set of numbers whose magnitude never exceeds 1. Okay, these are same as local coordinate system, okay, but being expressed by dimension set of numbers. Okay, so these are the notations. Okay, if it is in x direction, it is denoted by xi. Okay, this term is pronounced as xi. Okay, this as neta and this as zeta. Okay, okay, you can see if this is your 1D element, okay, having nodes 1 and 2. So at the center of the element, the value of this natural coordinate will be 0. In the left hand side, the value of that will be -1. On the right hand side, it will be +1. Okay, on right hand side it will be +1. Got it? This is about 3 coordinate systems in FEM: global coordinate system, local coordinate system, and natural coordinate system. Okay, natural coordinate system. Let's take down. So from next slide onwards, we'll start with the derivations. First, we'll define what is a shape function. Okay, then we'll start with the derivation of shape functions for 1D element. Okay, 1D bar element. That is this one. Okay, in terms of global coordinate. In terms of global coordinate means in terms of x and y, x, y, and z. If you take it with respect to local coordinate system, if they tell you to derive it with respect to local coordinate system, it is x dash y dash. Okay, if they tell you with respect to natural coordinate system, it is with respect to xi, neta, and zeta. Okay, xi, neta, and zeta. So this is pronounced as di, this as neta, and this as zeta. So most of the times what will happen is most of the people pronounce this as zeta. Okay, but this is xi, xi. Okay, this is neta, and this is zeta. Okay. So in the first module, second half, you have derivations of shape functions for simplex elements, 1D, simplex 1D, 2D, and 3D case in terms of global coordinate systems, in terms of x and y. Okay, we'll derive those. Now again, before moving on to derivation, okay, so there is a relationship between global coordinate system and natural coordinate system, because in most of the problems you will be using that while deriving also, okay, in the coming chapters, coming modules. So you should know what is the relationship between global coordinate system and a natural coordinate system. Okay, even that can be asked for you in the exam for 4 marks. Should I move to the next slide?
No, sir.
Okay, you can take down.
Sir, can you tell that notation once again?
Which one? This is xi. This is xi. This is neta. This you might have used. Okay. This you might have used. And this is zeta. And what happens most of the times, this is pronounced as zeta by most of them. But when you Google it and see, when you see the mathematical notations, right? This is xi, this is neta, and this is zeta. So this is like this, like this, like this, like this, and this is only one. Okay, this is 2 times. Okay, this is only once. So if you are doing it, if you are deriving the shape functions for 1D case, in case of natural coordinates, you will only have xi. If you are doing 2D case, you have xi and neta. If you have third case, you have xi, neta, and sorry. If you have 3D case, you have xi, neta, and zeta, all 3.
So you can proceed now.
Yeah. Should I move to the next? Yeah. you can take down the heading, relationship between global coordinate and natural coordinate, and take down these three figures one below the other. Okay, so first let us consider a 1D element, okay, having two nodes 1 and 2 in terms of natural coordinate. This is called as 1D element, or we can even call it as bar element since it is one dimensional. And write the values of the natural coordinate as it is said to you, its value does not exceed more than 1. Center, the value is 0, and on both the sides, on the left hand side it is -1 and on the right hand side it is +1. So when you are in the second figure here, when your displacement, your field variable varies, okay, it will vary in this fashion, or this is just written like this in terms of graphical fashion here. Okay, so -1 +1 here. Okay, same thing, 1 unit at the downside here, 1 unit on the upside on the node 2, and that those two are being joined passing to the center here. Okay, and in the third diagram here, what has been done is, this is -1 here, xi equal to -1, not +1 here. This is xi equal to -1. So in the third figure, what is done is, it has been drawn with respect to global coordinate as well as natural coordinate both. Okay, so +1 is added to all three in the second figure here. If you add +1 to each and every point here, this point, and this point, this is what you get, right? This is what you get. And this point which has been written here, it is not this point. Okay, it is somewhere in between, whose value is xi +1. Okay, whose value is xi +1. Just xi has been added here. Okay, as good as 1 is added here, here, and here. Okay, you will get a triangle form, and let me denote that triangle: A, B, C, D, and E. Okay, using the similar triangle concept, we will derive what is the relationship between a global coordinate and a natural coordinate. Global coordinate and natural coordinate.
Sir, can you explain the same thing once again?
So first you draw a 1D bar element, okay, denoted by two nodes 1 and 2, and this has been drawn in terms of natural coordinates, okay, whose value does not exceed 1. So write the value of xi. If this is your element, okay, in the center of the element your natural coordinate value will be 0, and on the left hand side it is -1, on the right hand side it is +1. The same thing has been drawn here in the second figure. -1 is taken below here, okay, +1 is taken upside, and this has been drawn as you draw SFD BMD, right? Same way, just it has been drawn here. Okay, and +1 is added to each of these cases. +1 here, +1 here, +1 here. What will happen if you add +1? If you add +1, what will happen? This xi will be equal to what? 0. So it will be here. So this will be xi +1. Okay, this will be xi +1. Don't take your 0 again. Okay, this is just a representation. Actually it is 1. Okay, actually it is 1, but we are not taking exactly here in this third figure, anywhere in between. Okay, after this point. Okay, after this point will be xi +1, right? Now if you add 1 here, what will be this here? Xi will be equal to 2. Xi will be equal to 2, and there is a reference point here, reference which has been considered, and this, from this reference to this point, node 1 is called as x1, and from this reference to node 2 is called as x2, and this distance where it is represented as xi +1 is a distance x, anywhere in between the element. Okay, anywhere in between the element, and just a triangle is formed. Okay, so here this distance is x1, this distance is x2, and what is x2 minus x1? What is x2 minus x1? It is nothing but, is it nothing but the length of the element?
Yes, sir.
Okay, it's been written here. See, where x2 minus x1 is denoted by LE. Okay, L and prefix will be E. Okay, prefix will be E. So it is nothing but length of the element. See, now all the problems while deriving will denote length of the element as LE. Okay, LE. So which is given by x2 minus x1. Okay, from a reference point. Okay, so this x1, x and x2 are nothing but your global coordinates. Okay, representation in terms of global coordinates, and this xi -1 to +1 is a representation in terms of natural coordinate. Even here, okay, here xi equal to 0, now here xi equal to 1, okay, here xi equal to 2. Okay, but xi will not vary, but xi will not vary up to, it will not exceed 1. This is just to get this relation. Okay, this just to get the relation, we are forming a triangle here. Okay, just to get a relation, we are forming a triangle here. Okay, we are forming a triangle by adding 1, to each case. Okay, here, here and here. Okay, got it? Someone was asking a question.
Sir, is that -1 or +1?
Which one? This
In
one,
the
right?
middle diagram.
This is -1. This is -1.
Okay, sir.
This is -1. Okay, and this x1, x and x2 are nothing but your global coordinates in terms of global coordinates. Now, if you take a similar triangle concept, that is ABE and triangle ACD. So AB by AC, that is AB by AC equal to BE by what? DC. What is AB? What is AB? Is it x minus x1? Is it x minus x1? And what is AC? Is it x2 minus x1?
Yes, sir.
So this has been written with respect to what? Global coordinate. Now this is with respect to what? Natural coordinate. So what is BE? What is BE? Is it xi plus 1? And what is DC? Is it equal to 2? Okay, right? Now just simplify this. 2 you take it on that side, okay, and -1 you take it on this side. So you will get xi equal to 2 times of x minus x1 divided by x2 minus x1 minus 1. Okay, this is the relationship between a natural coordinate and a global coordinate. Okay, so this is your natural coordinate xi. So this natural coordinate, if you are converting it from one coordinate system to other coordinate system, so this xi will be equal to 2 times of x minus x1 divided by x2 minus x1 into, sorry, minus 1. Okay, minus 1. So this is your relationship between a natural coordinate and global coordinate. Only one step. Okay, just by applying the concept of similar triangles. Okay, just by applying the concept of similar triangles. Now what is this x2 minus x1? It is nothing but LE. Even this can be written like this, or even you can write it this way. And in most of the derivations you might come across dxi by dx or dx by dxi. So when you differentiate this equation 2, okay, with respect to x, okay, with respect to x, so with respect to xi here and with respect to x here, so here dxi equal to 2 times of, if you differentiate this term, x1 is a constant, okay, x1 is fixed, it's a constant. So when you differentiate x, you will get d of x, okay, and this will LE will remain as it is, minus, so this differentiation is 0, so this is what you get. So dx upon dxi will be equal to LE by 2. Even this question can be asked in the Viva question during your FE lab. Okay, what is the value of dx upon dxi or dxi upon dx? Okay, that is your relationship between global coordinate and natural coordinate, because we will be using this when we are converting it from one form of one coordinate system to other coordinate system, right? Especially when we are using from global to natural, natural to global, we will be using this. Okay, we will be using this. If it is dx upon dxi, we will be using LE by 2. If it is dxi upon dx, we will be using 2 by LE. Okay, 2 by LE. This is the relationship between a global coordinate and natural coordinate. Even this can be asked. What is the relationship between natural coordinate and global coordinate? So you have to tell this equation xi equal to 2 times of x minus x1 divided by le minus 1 because we'll be using this in the derivations at the later stage, not in the derivations of shape functions for 1D and 2D. Hope you got it.
Yes, sir.
Okay. Take down and then we'll move on to the shape function and derivation for 1D case. Tell me once you finish, okay?
Sir, done copying, sir.
Yeah. And move to the next slide. This I have to delete it. Okay. Wait a second. So this is shape function. This is shape function. So what is the shape functions are defined as the interpolation functions. These are nothing but interpolation functions only. So whatever you assume a polynomial function, right? They are them only. But once we derive it, we'll get another form of equation. Okay. Using those interpolation functions. Okay. Another form of interpolation function, but in terms of shape functions. Okay. Shape functions are defined as interpolation functions used to interpolate the value of the field variable at any point within the element in terms of the nodal values. Okay. Now, once you finish your finding the displacements, unknown displacements u1 and u2 at these nodes, now you are asked to find out what is the displacement at x equal to somewhere in the element. At that time, these shape functions are very helpful. Okay, that time these shape functions are very helpful. By using the polynomial functions u equal to a0 plus a1x, can you find out if I give at x equal to so much, but you don't know what is the value of a0 and a1, a0 and a1, you will find out the value of a0 and a1 by applying the boundary conditions, rearrange the equation, okay, such a way that in terms of n1 and n2, so those are called as your shape functions. Okay, those are called as your shape functions. So shape functions are defined as interpolation functions used to interpolate the value of the field variable at any point within the element in terms of nodal values. Okay, we'll derive the 1D simplex element shape function, then we'll solve a problem on that. You'll come to know. Okay, one problem on each, derivation one and one problem on each. Okay, you can take down the definition. Okay, and take down the heading derivation of shape functions for 1D simplex element, okay, in terms of global coordinates. If in the exam, if they ask you derive the shape functions for 1D element, only 1D element, if they ask 1D element in terms of global coordinate, you have to derive the same. Okay, in terms of global coordinate, you have to derive the same. They may not mention what simplex element. Okay, they may mention or they may not mention. If they mention for 1D element in terms of global coordinates, you have to derive this same derivation. Okay, same derivation. So you can take down the heading, derive the shape functions for 1D simplex element in terms of global coordinates. Okay, in terms of global coordinates, and take down this figure. Okay, wherein a 1D element is shown with nodes 1 and 2. You will have a shape function n1 at node 1 and a shape function n2 at node 2. Why the name shape is because it will define the how your displacement varies within the element. Okay, that's why it is called as shape function. Okay, whether it varies linearly, whether it varies quite parabolically, it will tell you that. Okay, now since we are considering all linear cases, all the displacement of field variables vary linearly. So draw this figure. Okay, so whenever it has been told you draw solve it in terms of global coordinates, you have to mention this. If it is natural coordinate, you have to mention, you have to draw this previous one, first figure. Okay, wherein you indicate xi equal to -1 on the first node, xi equal to +1 at the second node, and xi equal to 0 at the center node. Okay, at the center of the element. So this one you take the element indicating two nodes 1 and 2 and show n1 and n2 there. Okay, so u1 is the displacement at, these are the given values now. Given these are nothing but the boundary conditions which are given. Okay, so u1 is the displacement at node 1 and u2 is the displacement at node 2. Okay, and this is your x1 from a reference. Okay, this is x2. x2 minus x1 is nothing but length of the element le, and this is x. Okay, anywhere within the element, anywhere within the element. So let us consider 1D bar element having two nodes 1 and 2 respectively, and each node there is single degree of freedom. We are not considering 2 degrees. Okay, we are considering only single degree of freedom per node. n1 and n2 are called as shape functions for node 1 and node 2 respectively. u1 and u2 are nothing but your displacements. Okay, so they are called as nodal displacement because they are the displacement of these particular nodes. Okay, so they are called as nodal displacements at node 1 and 2. x1 and x2 are distance of node 1 and 2 from origin O. Okay, and x is the distance of any point within the element from origin. Okay, from origin. So since this is a 1D element, okay, what was the equation for 1D simplex element? Polynomial equation, u equal to u of x equal to a0 plus a1x. So let us assume the displacement as u equal to a0 plus a1x, and let us call this as equation 1. Okay, and u is the displacement at any point. So u1 and u2 are the displacement at particular nodes, and u is the displacement at anywhere in this point at x. Okay, at x. And whereas a0 and a1 are generalized coordinates, so in order to find these generalized coordinates a0 and a1, we will be applying the boundary conditions. Okay, we will be applying the boundary conditions. So what are the boundary conditions? We will see it in the next slide using this figure only. And take down this and let me know. First you have to start it like this. Okay, draw a figure, okay, draw the element, show all the notations, write what it is. Okay, Write the notations. Okay, what are those? Then assume the polynomial function. In order to find out the generalized coordinates, we'll be applying the boundary conditions. Let me know once you finish taking it down. This is very important from exam point of view, this derivation, this and 2D case. Okay, 3D case might be rarely asked because it is little lengthier, but you should know how it is, okay, how it is derived, and what are the shape functions for 3D case as well. It can be asked, okay, it can be asked for more marks in the exam. Finish? Finish everyone?
No, sir.
Okay. Take one. So we'll apply the boundary conditions, one at node 1, okay, the other boundary condition at node 2, okay, boundary conditions at node 1 and node 2. So we'll again get two simultaneous equations. We'll solve those two simultaneous equations, get the constants, substitute those constants back in this equation, rearrange them, we'll get shape functions. That is how is the derivation. It will be same for even 2D case as well, okay, only the number of equations will increase, simultaneous equations will increase. So here there are only two because there are two nodes and 1 degree of freedom per node. In the 2D case there are 3 nodes, so 3 simultaneous equations. In the 3D case there will be 4 simultaneous equations. Finish?
Yes, sir.
Okay. Now we have to find out the generalized coordinates a0 and a1. So in order to find out those generalized coordinates a0 and a1, we should know what are the boundary conditions. This is your figure, right? So at node 1, at x equal to x1, what is the displacement? U will be equal to u1. So at node 2, at x equal to x2, what is u? U is nothing but u2. So these are your boundary conditions. At x equal to x1, u is equal to u1, and at x equal to x2, u is equal to u2. So when you apply these boundary conditions and substitute in the equation 1, that is u equal to a0 plus a1x. When you apply this first boundary condition, okay, at x equal to x1, u equal to u1. So you will get the first equation, that is u1 equal to a0 plus a1x. Okay, u1 equal to a0 plus a1x. Wherever you have u, it will be u1. Wherever you have x, it will be x1. Same when you apply at node 2 boundary condition, at x equal to x2, u equal to u2. So u2 equal to a0 plus a1 x2. Okay, a0 plus, so u2 equal to a0 plus a1 x2. Let us call this as equation 2. Okay, equation 2. So once you get this two simultaneous equation, you have to solve this two equations simultaneously in order to find out the constants a0 and a1. So when you solve this simultaneously, take minus, minus and minus here, these two will cancel out. Okay, so in these two, a1 is common, so x1 minus x2 in brackets, and this is u1 minus u2. Okay, so I'll rearrange this. So you will get a1 equal to u1 minus u2 divided by x1 minus x2. Okay, minus has been taken common in both numerator and denominator. Okay, minus will become plus now. So you will get u2 minus u1 divided by x2 minus x1. Why it is done like this? Because it will be easier for us to write this x2 minus x1 at the last as length of the element, which is this one. Okay, which is this one. So once you get this a1, in order to find out a2, a0, what will you do? You will substitute the value of a1 in any of these two equations. So in the equation u1, it has been substituted. So in place of a1, you substitute this. Okay, in place of a1, you substitute u2 minus u1 divided by x2 minus x1 into x1, okay, plus a0. Now you want the value of a0, right? So this you take it on the other side. This is what you get. a0 equal to u1 minus u2 minus u1 divided by x2 minus x1 into x1. Now you expand this numerator. Okay, second term in the numerator. Okay, so you will get this, and when you take the LCM, this will come on this side. Okay, LCM is x2 minus x1. This will come on this side. So when you simplify that, u1 into x2, u1 into x1. So these two terms, and this one u2 into x1 minus minus plus. Okay, u1 into x1, and these two terms will get cancelled out. Okay, so you will get a0 as u1 x2 minus u2 x1 divided by x2 minus x1. Okay, divided by x2 minus x1. Did you get it till this here? First you listen to me. Did you get it till here? So first let me explain again. What are the boundary conditions? At node 1.
Explain again, sir.
Yeah. See, these are the boundary conditions. What are the boundary conditions? At x equal to x1. So what is your displacement u? U will be equal to u1 at node 1. At node 2, x equal to what? X, if you expand this, x will be equal to x2. What is the displacement at node 2? U will become u2. So these are your boundary conditions. At x equal to x1, u will be equal to u1. At x equal to x2, u will be equal to u2. You have to substitute these two boundary conditions in this equation 1. That is u equal to a0 plus a1x. So when you substitute that boundary conditions, that is at x equal to x1, u equal to u1. What is the equation which you get? u1 equal to a0 plus a1 x1. At node 2, x equal to x2, u equal to u2. So what is the equation which you get? u2 equal to a0 plus a1 x2. See here. Are you getting those equations? Got it till here?
Yes, sir.
Okay. Now we have to solve this simultaneously. I hope you know how to solve the simultaneous equation. Okay. Take minus here. These two terms will get cancelled out. A0 plus A0 minus A0. And this will be U1 minus U2, which is written here. Okay. And this is A1 is common. X1, which is plus sign, and X2 is in minus sign. X1 minus X2. Take this down. Okay. You will get A1 equal to U1 minus U2 divided by X1 minus X2. Okay, so since we know what is the length of the element, which is given as x2 minus x1, we'll write the denominator as x2 minus x1. Okay, we have to take minus common. If you take minus common both in the numerator and denominator, this will become u2 minus u1, and this will become x2 minus x1, and that is the value here. Okay, that is the value which is written here, because at the end of the equation we'll write this x2 minus x1 as LE, which is nothing but length of the element. Got it till here now? Got it?
Yes, sir.
Okay, now you got the generalized coordinate A1. Now you have to find out what? A0. How will you find out A0? You have to substitute this A1 either in equation U1 or equation U2. Let us substitute this A1 in equation U1. When you substitute that, this is what you get. So U1 equal to U2 minus U1 divided by x2 minus x1 and x1 as it is plus A0 as it is. Now you take this term on the left hand side. You will get A0 equal to U1 minus U2 minus U1 divided by x2 minus x1 into x1. Now we'll take the LCM. If you take the LCM, what is the LCM? x2 minus x1 is the LCM. Okay, now you multiply that x2 minus x1 to this term u1. Is it? If you take u1 common in this first two terms here, are you getting x2 minus x1? This has been taken on this side and this has been expanded here. Okay, u1 into x2 and minus u1 into x1. Getting it? And this term is there, continuous, minus u2 into x1 minus into minus plus u1 into x1 divided by x2 minus x1. So this term and this term will get cancelled out, and these two terms get cancelled out. What is remaining? u1 x2 minus u2 x1 divided by x2 minus x1. That is nothing but your generalized coordinate A0. Okay, generalized coordinate A0. Got it? Got it, everyone?
Yes, sir.
Okay. Okay. You first let me explain the next part also. Now you got these two values, A0 and A1. Okay, A0 and A1 here. Now substitute these values of A0 and A1 back in equation 1. That is this equation. Back in equation 1. Okay. So it's here. So what is A0? This is A0 written here. What is A1? Okay, which is this one, and x, that is this one. So A0 plus A1 into x. Okay, now expand this. LCM is same. Okay, x2 minus x1, x2 minus x1. You can take the LCM and you can write x2 minus x1 as LE now. Now you have to write. Now rearrange this. So u1 x2 as it is minus u2 x1 as it is, and this you multiply u2 into x minus u1 into x. Now you have to take common u1 and u2 separately. Okay, u1 and u2 separately, and write divided by LE for both. Okay, u1 you take common. If you take u1 common, what will you get? x2 minus x. So u1 x2 minus x divided by LE, and this when you take u2 common, you will get x minus x1 divided by LE. Okay, x minus x1 divided by LE. So this is your equation. Now we call this x2 minus x by LE as n1, and we call this as x minus x1 by LE as n2. The coefficients of this u1 and u2 are nothing but your shape functions n1 and n2. Okay, these are your shape functions. See here, initially we assumed the polynomial function in this fashion. Okay, in this fashion. Again, once we get this generalized coordinates A0 and A1, we'll get another polynomial function, but in terms of shape functions n1 and n2. n1 and n2. n1 and n2. You will be knowing what is x1 and x2. Now if you are asked to find out at distance x, any value x, what is the value of u, you can easily find out. Okay, you can easily find out. This is how you derive the shape functions. Even for 2D case also you will derive it in this fashion only. For only cases, instead of 2 equations here, we will get 3 equations. You have to find out the generalized coordinates a0, a1 and a0, a1 and a2. For 3D case, a0, a1 and a2 and a3, like that. Did you get this? Did you get the simplification? Okay, you can take down. Okay, these are nothing but your shape functions. In the Viva questions also it might be asked, what are the shape functions for 1D bar element in global coordinates? You have to tell n1 equal to x2 minus x divided by LE and n2 equal to x minus x1 divided by LE. Okay, there is one more slide. Then we'll wind up today's class. Problem we'll do it in the tomorrow's class. Understood, right? It's the same concept, all the derivations. Okay, even in terms of natural coordinates also will derived in the same fashion only. Okay, same fashion. We have a polynomial function. We have polynomial function in terms of global coordinates a0 plus a1x. If it is in terms of natural coordinates, in place of x it is xi. Okay, again we have to apply the boundary conditions and find out, okay, the shape functions. This same procedure is followed for almost all the derivations. Okay, almost all the derivations. Only the number of equations based on the element will increase, and the expressions for shape functions will change. These are your shape functions: x2 minus x1 divided by L length of the element, and x minus x1 divided by length of the element for 1D case in terms of global coordinates for 1D bar element. So what are the shape functions for 1D bar element in terms of global coordinates? So they are n1 equal to x2 minus x divided by LE, n2 equal to x minus x1 divided by LE.
Sir?
Yeah?
Sir, what is the difference between u1 and x1, sir? Sir, actually here u1 nodal displacement at node 1 is there,
Yeah,
sir.
u1 is nodal,
And x1,
and this is x1 is not the displacement, it is the distance of that node 1 from the origin. So when you apply a force to this element, this node 1 will displace by distance u1 and this by u2 displacement, and this is the distance. Okay, this is the distance from the origin, from a reference origin. Got it? These are not the displacements. Okay, these are your coordinates, coordinate systems. X. So it will be x1 at node 1, it will be x2 at node 2. Got it? u1 and u2 are the displacement, x1 and x2 are not the displacements. Okay?
yes, sir, got it.
Okay?
So explain the last step.
This one?
Yes, sir.
Okay, so you got values of a0 and a1, right? Okay, up till here did you get it? Okay, now once you get this values of a0 and a1, what you are supposed to do is you have to substitute this value of a0 and a1 in equation 1. You can see it, substituting the values of a0 and a1 in equation 1. What is that equation 1? Your polynomial function which you assumed. It is there in your previous slide. Okay, it is there here, which is u equal to a0 plus a1x. Okay, substitute the value of a0 and a1. See, this is a0 and this is a1 and this is x as it is. Okay, you can take the LCM, okay, and write x2 minus x1 as length of the element, which is LE. And now take common what? u1. So when you take common u1, what will you get? x2 minus x, right? x2 minus x, and write it separately and divide it by LE. separate the two terms, one with respect to u1, one with respect to u2. Okay, even if you take LCM, you will get back this equation again. So if you take u1 common, x2 minus x divided by length of the element, because it is common for all the terms. Okay, next you take u2 common. If you take u2 common, x minus x1 divided by length of the element. These values which are there, the coefficients of u1 and u2, the coefficients of u1 and u2 are nothing but your shape functions n1 and n2. Okay, shape functions n1 and n2. Okay, so this is also your polynomial function only. Okay, your interpolation function only, but in terms of shape functions n1 and n2. So there it was in terms of polynomial function and in terms of global coordinates x. Now the same equation, after applying the boundary conditions, you got it in this fashion now. Okay, you got it in this fashion. So in terms of shape functions n1 and n2. Now once you solve the problem, you will be knowing what is the displacement at node 1. Okay, that is u1. You will be knowing what is the displacement at node 2. Okay, and you will be knowing what is x2 and what is x1 and what is the length of the element. And you are asked to find out at distance x, somewhere x, okay, in the element, you find out what is the displacement. Substitute all the values, you will get what is the displacement at that position, okay, at that point. So this is the importance of shape functions. This is the importance of shape functions. Got it now? So where n1 is x2 minus x divided by LE and n2 is x minus x1 divided by LE. So this is the importance of shape functions. Okay, you will find out the displacements or unknown field variable at nodes, but when you are asked to find out anywhere within the element, so these shape functions are helpful. You know what is u1 and u2 after solving. You will be knowing what is x2, x1 and length of the element, and you are asked at distance x, some value x, find out what is the displacement. Substitute all the values, get it. Okay, so that is what is the definition, shape function. You can see here in the previous slide. Shape functions are defined as interpolation functions used to interpolate the value of field variable at any point within the element in terms of nodal values. In terms of nodal values means what? These are your nodal values, u1 and u2. Okay, u1 and u2. Got it?
Yes, sir.
Okay. Still it is not complete. The derivation is not yet complete. This is over, but we have to see the variation. Now when you substitute the value of x, how your shape function will vary from this point to this point. Quickly, because another time is not there now. Let me move on to the next slide. I'll share this, okay, later on with you. Now this is the equation, third equation, u equal to n1 u1 plus n2 u2. So this equation, we'll write it in matrix form here. You can see here u, okay, equal to n1 n2, which is the row matrix, and u1 u2. If you multiply these two, row into column, you will get back this equation. And in short, we write this like this: u, that is nodal displacement matrix, and then is shape function matrix, and q, sorry, yeah, these are also nodal displacement matrix. This is your just displacement at x, any point x, and this is your nodal displacement matrix. Okay, n into q, and this is your variation of shape function n1 and n2 for 1D bar element. This is individual variation and this is combined variation. Let's see how this graphs have come. First you draw the element 1 and 2, okay, for both the cases, for third case also. This has just been combined here, okay. This triangle has been drawn here, this triangle has been drawn here, okay. Now how this, you get it like this. Now in the first equation here for n1, at node 1, when you substitute x equal to x1, at node 1, what is x? At node 1, what is x? At node 1, what is x? Is it x equal to x1? When you substitute x equal to x1 in both n1 and n2, what will you get? What will you get? If you substitute x equal to x1, if you substitute x equal to x1 here for shape function n1, will you get x2 minus x1? Yes, which is nothing but length of the element LE.
Then n1.
Okay, both LE will cancel out. What is the value of n1 then?
0.
1. x2
1.
minus x1, length
1.
of the element. LE will cancel, you will get 1, right? Now same here, when you substitute x equal to x1 for n2, this will be 0. You can see here that has been written in.